Welcome back to Math 104. Compute the probability that with 8 people in the room, if each one randomly picks a whole number from 1 to 50, there is a shared number among them. Before we compute, let's notice two things about this problem. One is the direct analogy to the birthday problem. Mathematically, this is just like the birthday problem, except that each person has only 50 possible whole numbers to pick, as opposed to 365 different possible birthdays. The other thing to notice is that we are asked for the probability that there is a shared number among them. Not that the numbers are distinct, but that the numbers are not all distinct from one another. So we must find 1 minus the probability that the numbers are all distinct from one another. To compute the probability that these 8 people all pick distinct numbers, let's understand the experiment. It is an 8-stage experiment. There are 8 slots. And within each slot, there are 50 possibilities for how each person could pick their number. Each one has 50 choices, and therefore the denominator will be 50 to the 8, but I'm writing it out in gory detail here to really emphasize the nature of the experiment. It is an 8-stage experiment. If we have 8 stages in the denominator, we should have 8 stages in the numerator as well, because that's what the experiment is. It is an 8-stage experiment. As in the birthday problem, there are 50 ways that person number 1 could pick a number, such that the outcome still counts towards the event in question. There are 49 ways that person number 2 could pick a number in light of how person number 1 has already picked. And so on down the line. Notice that by the time we've written out all 8 numbers in the numerator, the last number to appear, 43, is not 8 less than 50, it's 7 less than 50. If you counted up from 43 to 50, there would be 1, 2, 3, 4, 5, 6, 7 increases, but 8 numbers. So it makes sense that 50 minus 43 is only 7, but there are 8 numbers here. When we compute this probability that there is a shared number somewhere among the group, we obtain approximately 0.4458. That means, when we go on to ask which is more likely, that there is a shared number among them or that there isn't, it's more likely that there isn't. This is the probability that there is a shared number among them, that 2 or more people have guessed the same number. This is a little bit less than a half, so it is a little bit more likely that the numbers are all distinct. But it's still reasonably likely that there will be a shared number in this group. In fact, if you increased the number of people to 9 and redid the whole computation, then this probability would cross the threshold and go above 0.5. With 9 people in the room, it would suddenly become more likely than not that they did manage somewhere among them to have a common number. Not that they would all have the same number, but that there would be some pair of people who had guessed the same number. What is the significance of what we have just done? What we have found in these examples is that with a relatively small number of people in the room, whether comparing birthdays or guessing numbers, with a relatively small number of people in the room, it is more likely than not that there will be a shared birthday, or that there will be a number that 2 people guess. The conclusion is that seemingly remarkable coincidences are actually not so remarkable at all when we compute the probability that they occur just by chance. When it turns out that you're in a room with 40 people, and you all go around saying what your birthdays are, and it turns out that, oh my gosh, there are actually 2 people who have the same birthday. What a coincidence! It's actually not so remarkable at all. We have the multiplication principle to thank for being able to compute those probabilities and realize this conclusion. We'll look at some more coincidences at the beginning of the next set of videos.